Hello. The title of this lecture is The Scientific Revolution. During the late 1500s and 1600s, impressive advances occurred in the field of science. This scientific revolution represents a period when scholars and scientists increasingly accepted the importance of experimentation and mathematics. In adopting a new mechanical conception of nature, scientists use mechanics to explain the laws of nature. The scientific method of observation and experimentation brought new knowledge that would eventually transform the world. The scientific revolution was an evolution rather than revolution. Some important technological advances had taken place in the centuries before the scientific revolution. And this included what took place in China. The Chinese centuries before they appeared in Europe, there was the printing books. The Chinese were printing books before the Gutenberg press appeared in Europe. And Chinese sailors had the compass before Europeans were using the compass. There was gunpowder in both China and India before it became known to the Europeans. However, the Europeans were expert in developing many other technologies, and they provided a nurturing environment for creativity. Give you a quote from the economist Thomas Sowell. He argues that, quote, while ideas have been historic in their consequences in science and technology, ideas by themselves have not been enough. The receptivity of a giving culture to ideas and innovations and the ability of that culture to take these advances and carry them further had been crucial. End of quote. What Sowell here is arguing is that it's very important to have a nurturing environment for ideas. There has to be a will and acceptance for there to be certain things that would unfold during the scientific revolution. And these, which I will list at the end of the lecture. European medieval thinkers tended to be more interested in finding out why things happen rather than how. They believe that God is the first cause of all physical phenomena. However, there was much intellectual activity during the medieval age, even though much of it probably wasn't appreciated by Enlightenment thinkers. So again, getting back to the idea of the scientific revolution, it's not as though the science sort of sprung out in the 1500s and 1600s. There had been some very important discoveries that took place in the medieval period. I want to give you one example of an impressive work is the thinking of Robert Grosseteste. And he was born approximately 1178 and he died in 1253. Robert Grosseteste was the Bishop of Lincoln from the year 1235 until his death in 1253. Although he fell short in his attempt to determine a quantitative law of refraction, he did exciting work in the field of optics. And actually, before his work on optics, Grosseteste wrote commentaries on the physics and posterior analytics of Aristotle. Grosseteste wrote that investigations must start with observed facts, followed by an attempt to determine what caused those observed facts. the term hypothesis would not be coined for another 400 years, but he, in essence, invented it. Grosseteste saw the importance of resolving the causes into their component elements. Next was to derive a set of expectations that allowed the researcher to reconstruct the phenomena. When experience contradicted expectations, then there had to be a rethinking of the expectations. It was a major step for investigators to frame their research in a way that they could be proved wrong. So this was some very important work done in the period of scholasticism. During the Renaissance, scientists understood the word experiment to mean putting something to the test. One did this when one observed nature. In the 1500s, there was recognition that phenomena observed under controlled conditions could be the same as what took place naturally. One field that experienced a major transformation was the understanding of Earth within the universe. Since the 2nd century, the geocentric theory of the universe had dominated. This was the idea that Earth was fixed at the center of a series of concentric spheres. The Polish priest Nicholas Copernicus in 1543 argued for a heliocentric theory that the sun was motionless in the center of the universe. So something very different than previous centuries. Not the Earth in the middle, but the sun. And the planet revolved around the sun, and the Earth's moon also revolved around Earth. There were flaws to Copernicus' model. It failed to make any improvement on predicting the location of the planets. Nonetheless, his work provided another way of confronting some of the difficulties inherent in geocentric theory. German Johann Kepler made significant improvements to Copernicus' work. Kepler abandoned the circular components of Copernicus and instead portrayed the orbital paths of the planet as elliptical. A major turning point in the history of science was Italian Galileo's work on falling bodies published in De Montu. Born in 1564, Galileo represented the new spirit of inquiry that led to the rise of modern scientific method. One scholar wrote that Galileo, quote, reported his experiments with a level of detail and meticulousness that set a standard for natural philosophers thereafter. His experiments were controlled. Under consistent conditions, he observed falling bodies. Interesting, in the modern period, there were some who questioned Galileo's observation and data. When two objects were released simultaneously, Galileo reported that at the beginning, lighter objects fell faster than heavier objects, but heavier objects got faster, they sped up, and they hit the ground slightly sooner than the lighter objects. Now, how could this be? Was Galileo a poor observer? Did he make up his data? No, explained one scholar. Quote, in replications of Galileo's procedure, it has been found that when a light wooden sphere and a heavy iron one are dropped by hand, The lighter wooden sphere does not start out its journey. It does start out its journey a bit ahead. A natural, if misleading, consequence of the need to clutch the heavier iron ball more firmly than the lighter wooden one. This causes the iron ball to be released slightly after the wooden ball, even though the experimenter has the impression that he is opening his hands at the same time. Then, because of the differential effects of air resistance on objects of different weights, the iron ball catches up with and passes the wooden ball, just as Galileo reported. Galileo also demonstrated that mathematics was the language of nature. He concluded there were limitations on the accuracy of measurements of objects dropped from a height. Thus, he began using inclined planes to get more accurate measurements. Balls released on a plane rolled slow enough to get closer, more accurate measurements. His discovery of a systematic relationship between the distance traveled and the square of the day led to the first mathematization of a complex physical phenomenon. Of course, Galileo's most famous work was his construction of the first astronomical telescope that allowed him to verify Copernican theory that the Earth and other planets orbited around the sun. Galileo also observed that the moon's surface was mountainous. Overall, his work demonstrated the crucial role mathematics played in understanding the universe. The universe became subject to mathematical laws. Galileo wrote, quote, "Philosophy is written in that great book which ever lies before our eyes. I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. This book is written in the mathematical language, and the symbols and triangles, circles, and other geometrical figures without whose help it is impossible to comprehend a single word of it, without which one wanders through a dark labyrinth." End of quote. So here we have it, where Galileo is really stressing the importance of mathematics. Robert Boyle was another who made important scientific advances, notably the invention of an air pump, which he did in the year 1657. With his apparatus, Boyle simulated an atmosphere with progressively thinner air. Now, the one thing about this apparatus is now that one could do experiments on air pressure, and it did not require someone hiking up a high mountain. So this was something that allowed for additional research in this area. You could test a theory by this apparatus. Another investigator was Francisco Redi. Now he was the one who provided the first known use of a controlled comparison, and basically it was pretty simple. He sought to discern whether maggots, I know it's rather gross, but maggots whether or not they were spontaneously generated by a rotting carcass. And so what he did, he took two pieces of meat. And he put one piece of meat on a plate and just didn't do anything else, just left it there. It was open. And he took another piece of meat, but he covered it with gauze, and he also set that on the plate. Both of them just left out in the open. Now, what he observed was that the piece without any gauze developed maggots. And this simple experiment provided powerful evidence against the theory of spontaneous generation. The next step for these investigators, these science, such as Boyle and Galileo and Rene and others, was to report their findings. And the story goes that there was one professor who denied the planet of Jupiter. He denied that the planet Jupiter had moons, but he was unwilling to accept Galileo's invitation to come over and see for himself, to come take a look through my telescope to see the moons. And he refused. But this is, again, the point being here is, with all these discoveries, how can this information be disseminated? How can it be distributed in a way where there is going to be, serious discussion of them? And what we see is that without like formal scientific reports, there were greater chances of someone refusing to confront the truth. Robert Boyle's solution to communicate his findings to others was to provide a detailed account of the experiment, including everything that was done, and also any problems or any ambiguities of the experiment. Anything that might have arose. It became standard that scientists read and trusted scientific reports without having to necessarily replicate the experiment. And this body of trust. Trust is something really important, especially given when you have so many science reports that are arriving, that are coming as a result of numerous experiments, and one does not have the resources or possibly the time to even replicate a fraction of these. But if things are done legitimately and there is trust within the scientific community, there is much information that can be distributed throughout the science community. Now I want to turn to an Englishman, Francis Bacon. He was born in 1561 and he died in 1626. Bacon was one of the earliest philosophers to support the scientific method. He argued that knowledge was power and that knowledge could be obtained best by the inductive method of investigation. And induction is the drawing of a general conclusion from known facts. Bacon's most important achievement was to champion innovation and change. Rather than looking back to antiquity, rather than looking back to centuries before, he urged Europeans to boldly seek out new knowledge and understanding of nature. The best approach for an investigator was to examine the evidence of their senses before constructing logical speculations. One of his most famous passages from his books was as follows, quote, The men of experiment are like the ant. They only collect and use. The reasoners resemble spiders who make cobwebs out of their own substance. But the bee takes a middle course. It gathers its material from the flowers of the garden and of the field, but transforms and digests it by a power of its own. Not unlike this is the true business of philosophy. End of quote. Finally, Bacon drove home the point that increasing natural knowledge would lead to a better world. The pursuit of science meant material progress. In other words, the practical improvements of societies. And in time, science gained great influence in the public mind. And even today, we hear this often about following the science. French philosopher Rene Descartes regarded all physical phenomena as connected mechanically by laws of cause and effect. Now, one thing interesting about Descartes was that his starting point was doubt. Doubt. Here's what he wrote, quote, I immediately became aware that while I was thus disposed to think that all was false, it was absolutely necessary that I who thus thought should be something. And noting that this truth, I think, therefore I am, was so steadfast and so assured that the suppositions of the skeptics, to whatever extreme they might all be carried, could not avail to shake it. I concluded that I might without scruple accept it as being the first principle of the philosophy I was thinking. End of quote. Well, I think therefore I am is part of that phrase is would many would recognize it. Descartes' philosophy generated the problem of how mind and matter are related. Cartesian dualism refers to the absolute dualism between mind and matter. Quote, the mind cannot be doubted, but the body and material world can. The two must be radically different. History sees Descartes as the father of modern rationalism. Quote, using mind or human reason and its best instrument, mathematics, humans can understand the material world because it is pure mechanism, a machine that is governed by its own physical laws because it was created by God, the great geometrician. End of quote. Again, here we have, mathematics comes into the picture, the importance of mathematics with so many of these investigators, so many of these early scientists. And then there's Isaac Newton. Isaac Newton, born in 1642, and he lived in up to 1727. So he is one who actually his lifetime carries over into the Enlightenment period. So the latter stage of the scientific revolution and the early part of the Enlightenment. Now, Isaac Newton made huge steps in science. In Mathematical Principles in Natural Philosophy, this is his work that that was published in 1687. Newton explained his theory of gravitation and how the universe is held together. He defined three laws of motion that govern planetary bodies and objects on Earth. His theory explained why the planetary bodies continued in elliptical orbits around the Sun. The force of gravity or mutual attraction was the reason for every object in the universe being attracted to every other object. He was the greatest genius of the scientific revolution, and he presented a synthesis known as the Newtonian synthesis that, quote, created a new cosmology in which the universe was seen as one huge, regulated machine that operated according to natural laws in absolute time, space, and motion. End of quote. In addition, Newton championed empiricism, that one must observe phenomena before attempting to explain them. And certainly he was a great advocate of rationalism. Now, these are some of the key leading lights of the scientific revolution, but there are others. There are other important ones that I have left out on the lecture, but these would individuals would be on probably anyone's most people's short list as far as representing this period in history referred to as the scientific revolution. Now, I want to turn to several factors that explains the prominence of the scientific revolution, and this is again getting back to the earlier quote by economist Thomas Sowell, and the point that ideas are good, and but to see if good and beneficial ideas take the next step before we see them progressing just beyond what someone thinks up, and have it be accepted and shared and supported, nurtured. It made a difference, and what we find is that during the scientific revolution, most things were really in place that allowed for these ideas to be shared and eventually discussed, and many of them accepted. So there was no limitations by governments, although there were some exceptions. I should point out there were, and I'll mention this shortly, how the church was very wary, apprehensive about some of the things that were happening. For example, what Galileo and others were stating. But there are a number of factors that explains the rise and prominence of the scientific revolution, and these are not in any particular order of importance. My list is, I have nine items here, reasons or factors explaining the rise and the prominence of the scientific revolution. First, Renaissance thinkers and those who promoted rational critical thinking had stimulated scientific progress. If one goes back to the Renaissance period, just previous period before the scientific revolution, there was this period kind of foreshadowed and was some pioneering work and about ideas of using rationalism, rational critical thinking, and so this was did laid some of the groundwork for the scientific revolution, Renaissance thinkers. Second, the establishment of more universities. So as universities were being built and begun, we see that this all helps in what we see with the growth of science. More universities. There was more additional support for the educated, and also there was a recovery of Greek mathematics. All of these boosted the desire for scientific knowledge. It is true that new ideas were often slow to penetrate a university, but most of the scientists had a university education, and universities, a number of them did offer physical and financial support for scientific inquiry and teaching. So, point two then, the universities, and just greater support for education, and the importance of Greek mathematics. Point three, the printing press. The printing press gave a boost to the spread of knowledge. And just to give you an idea how the influence of the printing press. The printing press, Gutenberg, we're talking in the mid 1400s. Well, in less than 50 years after the introduction of Gutenberg's press, there were printing presses in over 250 European cities. So having the printing press was very important at this time when there is knowledge and data to be shared. Point four, there were the creation of a number of institutions and associations such as the Royal Society of London. This was, towards the end of the period of the scientific revolution. This was in 1660, and there was another one similar was the French Academy of Science, and that was founded in the year 1666. Well, these institutions provided the educated key forums for scientific discussion. Point five, it became more obvious that there was a practical benefits, practical side of science. There was, among some, the realization that science could solve practical problems. I mean, that could be something like navigational issues, map making. I mean, there was many things that could assist in just practical problems and that needed to be solved, and also just to carry out different human activity. Now, on this point, I should mention that a lot of what was going on here was really within a very narrow slice of society. This was, a very small portion of the population that were, part of a scientific community, and it would take significant time before a lot of the science was used, effectively transformed into, commodities and tools that could be used by, the masses, by ordinary people. So it took time, but still there was this realization that science could solve practical problems. Point 6. Science offered money-making innovation, particular better instruments for industry. And here again would be improvements, technological improvements, and we're not quite there at the start of the Industrial Revolution, but there is industry, and there is certainly entrepreneurs and other people in business are receptive to things that could improve upon their the productivity of their various activities. Now again, there was anything quite what we would see 100 years later with the Industrial Revolution beginning approximately in the mid 1700s in England, but there were the realization that there could be some more improved upon instruments, tools for that would relate to helping business and money-making innovations. Point 7, new discoveries captured the attention of people. Now, not many people, but still, the scientific instruments such as the telescope, the thermometer, and air pump, these generated greater interest in science. Point 8, and actually that's my last point. I thought I had 9. Point 8, Galileo and others had been condemned by Roman Catholic authorities for some of their work. But the rise of Protestantism may have resulted in more support for independent scientific inquiry. Now, this is something difficult to measure, but it stands to reason just the competition between Protestantism and Roman Catholicism would be, and also just how the Protestants would not have been quite as top down, controlling which we get a sense of when it came to the various Catholic nations and the power that the church leaders would have in maybe kind of hindering any kind of progress. And then I point to Galileo for as the example. Now, science and faith did not always have to clash. Not only were science and religion compatible, they were inseparable. Quote, the rise of science was achieved by deeply religious Christian scholars. For example, Galileo saw scientific theory and religious piety as compatible. And this is what Galileo wrote, quote, I think in the first place that it is very pious to say and prudent to affirm that the Holy Bible can never speak untruth, whenever its true meaning is understood. And later he talks about he believed God wanted humans to use their minds, and he declared, quote, I do not feel obligated to believe that the same God who has endowed us with senses, reason, and intellect has intended to forego their use by some other means to give us knowledge which we can attain them. End of quote. All right, to wrap things up, The scientific revolution represented a new way of viewing and understanding the universe. There was the argument that God has placed human beings in the world to understand it, and then, having understood it, to turn it to productive, practical use through rationality. And this was a quote. Studying nature was a way to better understand God. The advance of science was seen by the fulfillment of God's plan. Finally, the new scientific ideas, quote, were so impressive that they set the standard for assessing the validity of knowledge in the Western world, end quote. The scientific revolution was a major turning point in the history of Western civilization. It made its mark first in the West and then worldwide. Now, I want to conclude with a quote from economist Thomas Sowell. And this is a reminder of the human element of scientific data. Quote, scientific methods can be objective, but individual scientists are not. Mathematicians are not objective, but that does not mean that quadratic equations of the Pythagorean theorem are just matters of opinion. Indeed, the whole point of developing and agreeing to objective scientific methods is to seek reliable information not dependent upon the subjective beliefs of particular individual scientists, or on any hope that most scientists would be personally objective. If scientists themselves were objective, there would be little need to spend time and effort to work out and agree upon objective scientific methods. End of quote. Something to ponder. And yeah, that's it. Thank you.